Will the slides be published?
They are published. Long time ago. Okay, so welcome back, everybody. And this is the last lecture. So what I'm going to do is to repeat a little bit about the Green's function material, which you will find in these slides. And you have access to these slides through the GitHub address. And after that, we will be discussing a little bit about the format for the final exam. And we will also use that to repeat a little bit of what we have done through the semester. So the topic today is to try to wrap up this discussion about Green's functions. So I will rush through some slides, but I will also try to switch between the slides and the whiteboard in order to discuss a little bit more this equation, which is called Dyson's equation, which is a fundamental equation in Green's function theory. Now, in this kind of survey of Green's functions, we have not gotten that much in depth in the Green's function theories. So we haven't looked properly at these time evolution operators and the links with the Green's functions. So in case you are going to dig a little bit deeper when it comes to Green's function theory, we have listed one textbook by Nagel and Hollande, which has a lot of Green's function formalism. But then there is a more recent textbook by Dikhoff and Van Neck, which is called Many-Body Theory Exposed, which focuses essentially on Green's function theory. And that is actually a pretty good read, which I recommend. And if you wish to go more into the application of Green's function theory, both to systems of bosons, because they discuss bosonic systems as well, and fermionic systems, that is a pretty good textbook. So I'm going to show you that one. So let's just bring up the browser here, and let me just bring up the textbook. That's called Many-Body Theory Exposed. And it should be in the GitHub address as well as a PDF. So the textbook here is this one, and that is a textbook which focuses essentially on Green's function theory. And you can either buy it via Amazon if you prefer, or most likely you can find it somewhere else. So this is actually a pretty good textbook if Green's function theory is something you are going to work with. And it has, I know that some of you are also looking at systems of bosons, and this is a textbook which has many nice examples from bosonic systems. In this course, we have essentially just focused on fermionic systems. There is obviously always a limit to how much we can. Okay, so what I'm going to do now is just to bring up the whiteboard again, and then we are going back to the slides when we've gone through this whiteboard exercise. And one of the things I wanted to discuss is actually the equation which is called Dyson's equation, which you will encounter in many applications of Green's functions. And this allows us also to link with many-body perturbation theory, because often this equation is solved in a perturbative way, because some of these contributions, which you will see to higher orders, are contributions which are more difficult to solve, and it's often rewritten in terms of a kind of perturbative expansion. So one of the things which I wanted to bring back are the equations which we looked at last week for the so-called Green's functions. So let me just remind you quickly about what we derived last week. Sorry. So we had defined the Green's function. So this is the formal definition of the Green's function. And then what we did was to rewrite this in terms of an operator trick. which some of you may have seen. So this operator relation was A and B are two operators which don't commute. This is something which we can rewrite in terms of this relation here, A minus B. And we have two operators, A and B, which do not commute. And in our case, A was defined as E, and E is just a variable. So it's going to represent the incoming energy of two particles. And you will see why this is a very useful formulation, because you can use that as in terms of a scattering problem. You can think of an incoming particle with an energy E, which then interacts with a many-body environment, and then just gets scattered, for instance, and ends in a final state with a given energy. So the Green's function is something which, as we discussed last time, contains a complete information about the interaction between either one, two, or many particles with a given many-body environment. It doesn't need to be a many-body environment. It could just be the free scattering of two particles. And last week, we discussed this quantity, which was called the T matrix, which could be rewritten for one particle, two particles, and many particles. And then we defined B to simply be given by H of I. And in our case then, we could rewrite this Green's function in terms of the following expression. So I'm just giving you the final expressions which we went through. So we have the unperturbed Green's function plus the unperturbed Green's function multiplied with this H of I multiplied with G. And H of I is the interaction, and this G0, which is normally called the unperturbed Green's function, is something which we presumably can solve, because we know if we have a given basis and have the operator H0, we know that this H0 has a known eigenbasis. So this is typically a problem which we can solve like we did in many-body perturbation theory or in Hartree-Fock theory, that we have one part of the problem which can easily be solved. And then we can express the solution of the other more complicated equations, in our case, Schrödinger's equation for an interacting system, in terms of a basis which we can construct and which is orthonormal. Now, this equation here is an equation which we can rewrite in many ways. And one of the ways we rewrote that last week was in terms of this T matrix. So this is an equation which in some cases can actually be solved as a geometric series. So this was a G0, and then we had this T matrix, and I'm leaving out energy dependencies here. And this tau or T is the so-called T matrix. And this quantity tau is then given in terms of the interaction plus HI times this G0 times HI and higher order terms. So the quantities which we also started to look at last time was how we could solve this equation when we now look at the free scattering problem. What we are going to do now is to look at this equation here in terms of a single particle Green's function. And we can then replace this T matrix with something which is called the self-energy. So for single particle Green's function, this quantity which we have, this tau, is then replaced by something which is often labeled as a sigma. And in our case, this will be a quantity which depends on an incoming state, an outgoing state P, an incoming state Q, and it has an energy dependence. And what we are going to have then is a Green's function, which is now going to be a function of these states, P and Q. So this can be states above and below the Fermi level. And this is going to be given by the unperturbed one for P and Q. It's a function of the energy plus this G of 0 of P Q of E. And then we have this object sigma P of Q of E multiplied with G0 of P of Q of E. This equation which you see here is actually because you can rewrite this one in terms of a modified self-energy. So last week, we actually wrote this equation in terms of a slightly different quantity. So this is now given as a plus G. So last week, what we did was to manipulate these equations in different ways. And then we can multiply this with a sigma star. And I'm going to define what these quantities can be and multiply it with G of P of Q of E. So last week, what we did when we wrote these equations, which you see here, we can write it like this. And then you have a perturbative expansion in, you can have a perturbative expansion in G. Or alternatively, you can regroup these terms here in terms of the interaction and rewrite it like this. And then you have two known quantities. So these are normally translated into matrices in actual calculations. So you would have a matrix multiplied with this matrix because you normally discretize your basis. If you have a continuum of momenta, for instance, of a particle which gets scattered, then this continuum is normally discretized. And then these quantities become a matrix. This becomes a matrix. And then you have essentially matrix-matrix multiplications. This is when you're thinking of actual implementations of the equations. Normally, this has every stage here has a full set of intermediate states which are summing over. So you would typically include the completeness relation here. And in practice, what you do then is to perform an integral over momenta and time, or momenta and energy. This is a technical aspect which we are a little bit hiding under the carpet now. Now, when you look at the actual calculations of an equation like this one, or an equation like that one, at the end, since this represents an infinite series of contributions, you end up doing a perturbative expansion. So let's then use this to show how we can actually set up this equation and link it with many-body perturbation theory. But before we do that, this equation which you see here, like this one, is often written in a graphical way as follows. So graphical representation. So the Green's function, the exact one, would typically be written like this. So we have some P, or rather we have Q. We start with a state Q here. So we have Q and P, and this depends on a specific energy. So this is G. And that is given by the unperturbed case, which is normally just drawn as a single line. So this is Q, this is P, and it comes with an energy. So this is the G of 0. And then you can either multiply this with the unperturbed case. You have a G0 here, and you start with a state Q, and then you have a self-energy. So you end up in a state which we're going to label as a state S. And this is your self-energy. And then you continue, and you end up in a new state R. And then finally, you have the Green's function, which leads to the final point P here. So this sigma now represents different types of interactions. And as you saw, it depends on the operator HI, the interaction piece. So let's see how we can actually solve these equations in practice. So this is graphically the same as Dyson equation. You can extend this to more than one particle, etc., etc. Yeah. It's basically the same here, actually. Because if you can sum these terms to infinite order, then you have actually renormalized it. Alternatively, if you look at the expressions here, you can rewrite it either in this form, where you have the two unperturbed ones here, or you can just rewrite this one as we did last week in terms of a modified one multiplied with the full Green's function. And this one contains only HI. If you go back to the expressions which you see here, this T matrix contains only an expansion in terms of HI and the unperturbed Green's functions. So this is basically the equation you want to solve. And then what you end up with is the practical approaches. And in many cases, you are not able to sum these contributions to infinite order. There are specific contributions which can be summed to infinite order, and that would be equations of the type of a Tam-Dankov approximation, which we discussed a little bit earlier in the semester, or a so-called random phase approximation. And these are cases where you can actually get an analytical solution for these self-energy terms. But you would not have all the terms in there. So let's now look at the case of one particle which is interacting with a many-body environment. And at the end, the practical recipe is to use many-body perturbation theory to some order, and then simply calculate this sigma and use that as the approximation. So let's go back to many-body perturbation theory. So this serves also as a way to repeat what we have done, but then we're also adding a new feature. So what we are going to look at now is a system of a particle which interacts with a many-body environment. Okay, so the example here, because we want to stay with a single particle Green's function. So keep in mind also that this type of equation, which you see here, can easily be extended to many particles. But let's look at a single particle which interacts with a many-body environment. So the single particle case. So what we are doing now is that we have a system with n particles, which is in this state here. But then you can now think of one particle coming in and interacting with this system. So at a certain time, this is an n particle system. But what we are doing now is that we act with this operator. So you can now think of a particle coming from far away, and then it sees, it could be a nucleus, it could be an atom, or it could be a surface of a solid state material. And this electron or whatever kind of particle we're looking at interacts with the system. And now we're looking at this as an n. So this is an n particle system, but this one is an n+1 system. Okay. So what we're going to look at now is the way we can calculate these different contributions in many-body perturbation theory. So what we want now is the overlap. So we have the state phi0 of AA, and then we have our Hamiltonian with H, and then we have an A dagger of phi0. So this A, this single particle state we have here, does not need to be the ground state of the system. So in nuclear physics, a typical reaction could be a proton which interacts with oxygen-16. It's normally written like that. That has 8 protons and neutrons. This produces an intermediate state. So if I add 1 proton to oxygen-16, this becomes 17 fluorine. And then maybe after some time, this guy here gets kicked out, or this system is unstable. And then fluorine-17 decays by ejecting a proton, which we put as a proton prime, plus oxygen 16, which could now be in another state. So this is just an example of a reaction you can think of. So you have a system which has 17 particles all the time, so the number of particles is conserved. This has 17 protons and neutrons, and here you end up with 17 particles, protons and neutrons. So now we are peeling away the electronic degrees of freedom. We're only looking at protons and neutrons. So this 16 means that you would typically write this as 8 protons and 8 neutrons. This guy here has 9 protons and 8 neutrons. And then you're back. So you see the number of particles is conserved and the number of the protons is conserved throughout these reactions. So this is a typical example of a nuclear physics reaction where we can use this formalism. You could replace a nucleus with an atom or a molecule or a solid state system. And you could think of an electron being trapped in a semiconductor. And then after some time, this electron gets kicked out of the semiconductor. So another alternative is you having a surface with some smaller defects. And then you have an electron coming in. This electron gets trapped in here. And then after some time, so you could think of this as the surface of a semiconductor. And this has defects, which then create potential differences, which then could trap temporarily an electron. This is a system with perhaps a finite lifetime. And then after some time, this electron gets kicked out. And then you have the semiconductor, which has n particles here. Actually, this is often treated as an infinity. And then this electron gets out and keeps moving and living its own life, independently of the semiconductor system. That's another way of thinking what is going to happen now. But now, I'm just looking at the expectation value of this specific state for the energy. But I could easily change this state which you see here, this one. I could replace that one with a B. And that B could represent this state here, or this state here. So the Green's function formalism, although we are not going in that depth into the formalism, is a formalism through its quantities like the Green's function, and as we will see later, through the spectroscopic or the spectral functions, are quantities which contain all the information about these processes. So in principle, it's a very powerful formalism. The only problem is that in order to use the full power of it, you need to have the expression for the self-energy or similar quantities. And what we're going to do now is simply to look at what these terms may look like. First, with many-body perturbation theory. So when we do many-body perturbation theory, we know that if we calculate this one, what we would typically end up doing is to perform a perturbative expansion where the energy of that system, this E, is going to be given by the E0 reference plus delta E1 plus delta E2, etc., etc. Okay? So let's look at delta E1 for that specific case. So that's going to look like as follows. So I'm going to have phi 0, and keep in mind that you can change this AA to an AB. And then I have my famous operators, because now I'm looking at the contributions which I have from the Hamiltonian, which is tailored to a specific vacuum state. And the vacuum state now is the vacuum state which in this specific reaction would be given by oxygen 16. In this specific reaction here, it would be given, for instance, by the ground state of a semiconductor with a defect. So you can translate this to all types of kind of fermionic systems. Or if you prefer atoms and molecules, then you would simply replace this with an atom. It could be neon and the scattering of electrons, or neon, or argon, any of the noble gases, or any of the systems you're interested in. So when you now look at this delta E1, what you're going to get is the following. So if we now sit down and look at the contributions, and if we now look at this state phi, and then I'm going to write it like this with Fn of phi of A, where this phi of A is A dagger on acting on phi 0. I'm leaving out the reference energy because that's not interesting, because that's just a constant, right? So which we would add to the final energy. So we are now just looking at the contributions from the correlation energy. So the reference energy, which we calculated here, is something which is just a constant, and that depends on the basis set which we are using. And we assume that that's something we can calculate. And you will see also that the reference energy here is going to be pretty easy to calculate. So when we look at this term here, which is the one of the contributions to the first order term, we know that this is simply given by phi 0, and then I have my A, and then I have my sum over PQ, and I have the matrix elements P of F of Q, and then I have the operator AP dagger AQ, and then I have my AA dagger of phi 0. And I'm skipping the curly brackets, which I normally use to indicate that this is a contribution to the from the normal ordered operators. So what we need to evaluate then is an AA with an AP dagger, an AQ, and then an AA dagger. And this is pretty easy because we have particle states. So these are the only possibilities. So that gives us just delta A, delta P, and delta A n cubed. So the first term, phi A of F of n, or phi A, is simply now given by the term which is going to be given by A of this guy A here. Now, this is again the same as H0 of A, and normally this term would then enter the reference energy, and we just leave it out. So this term here, we would add this one to E0 ref, which is the energy of the n particle system. So we add one unperturbed energy on top of that. So this would actually give us E0 ref plus epsilon A. If A is an eigenbasis, if A is an eigenbasis of H0. So that is now the new reference energy. It's the reference energy of the n particle system plus one particle in that specific state. But then what we have next is the guy here, which now contains a sum over all the states below the Fermi level. And then I have my A of I, of V, of A, of I, anti-symmetrized. And we know how to calculate that one. So that means that what I would have then, in diagrammatically, this is the same as, if we look at a diagram, so I have a state A coming in, and a state A leaving, and then I have my whole state, I here. And I'm just using that one as a Hugenholz diagram, so which means that this diagram can either contain the exchange part or the direct part. This defines, if we go back to the Green's function formalism, this is going to define the self-energy to first order. So this defines also the self-energy sigma of P of Q at a given energy E. So this is going over to a sigma of A and A at a given energy E. And this is going to be given, it's going to be slightly different when we do the Green's function formalism, because it will include a specific energy dependence, which we in many-body perturbation theory do not have. And that's simply because this term here in Green's function theory gets multiplied with a Green's function, which is energy dependent. But the building block is actually this diagram here. In many-body perturbation theory, with the way we wrote it, there is no energy dependence here unless the Hamiltonian has a specific energy dependence. So this term here defines actually this self-energy, the first order. So what you would have then would be a Green's function, which is not written like this, G of A, and then I'm going to put in a state, which I'm going to call for P here, of an energy. This is 0. And then it contains this self-energy, sigma. And then it has a state P here, but when we are integrating up, there is an integral over time or energy, which is involved here. So we are performing an integration, which I'm in a way hiding for you guys, because I'm adding a Green's function here, G of a state Q of A with a given energy E. And this term here is now the self-energy, which depends on P and Q and an E. And this self-energy to first order is normally written like this. This is in a more compact way here, where we now have the state where P and Q, they go over to the state I, but at the same time, there is an energy dependence here due to the Green's function. So you could now think of you setting up this diagram here, represented in terms of a matrix, and then you multiply this with the Green's function G0 and G0 here. So that's the basic difference between what we do in many-body perturbation theory and with Green's function theory. So what is often done is that people use many-body perturbation theory to calculate these different terms. If you then go to second order, then you will obviously have more terms. So to second order, and let us remind ourselves about what that might look like for this specific state. So to second order, the delta E2 for the one body system is going to be given by a sum over the intermediate states. And then I have my state now, which is a phi of A. And then I have my Hamiltonian, Fn plus V of n. And then I have my phi m here, multiplied with phi m. This is just as we did before. And then we have the Hamiltonian again, Vn plus, so these normal ordered terms of phi of A, divided by the energy epsilon 0 of A minus E of m. This is many-body perturbation theory. Just one small thing here before we move on to the calculations and see what kind of diagrams. So this is also an application of many-body perturbation theory. But instead of looking at a vacuum-to-vacuum expectation value, we are now redefining our many-body system to be a reference state with one added particle. You can easily see now that you can extend this to a reference state with two added particles, three added particles, etc., etc. So if you now go back to this first order term, which we put up here, this is actually a term where we actually only evaluated with respect to f of n. What about the two-body piece? If I plug in v of n here, why didn't I set it up? I didn't set it up because it's 0, but why is it 0? Any good suggestions? If I take the two-body term, let me give you a small aside here. So as a small digression, so what we had then, so this is for the one body term to first order, and then I would have a sum over PQ, and then I have my AP, and remember now that these are normal ordered with respect to the new vacuum state. So what I'm doing is actually to sneak in an element of repetition while we are doing Green's functions. So this is what we would calculate to first order. So why doesn't this give any contribution? I can obviously do this contraction. This is a viable contraction. These are particle states. Then we have Wick's generalized theorem. Yeah. You cannot do this. So this contraction which you see here, this one is not possible, is zero. It's only for these modified vacuum states when you have a normalized operator. That's a very important point. Yeah. Okay, so this means that the two-body term in that specific case does not contribute. But when we now go to intermediate states here, we can actually have contributions from both the one-body operator and the two-body operator. So if we look at the one-body operator, what could happen now is that one of the intermediate states could be a particle excitation of this true vacuum. So we could now think of one of these guys, this phi of m, that could be given by some A of B acting on phi 0. Okay, that's one possibility. Then we know that this phi of m, so this would be just a one particle state. I could have a one hole state. It is a possibility, but it's a possibility which is going to give us 0. I have another intermediate state which I could try out. And this intermediate state could be, because what I want now is a system which has one particle added to the reference state. Okay? So what I could have is a two-particle one-hole excitation. So this is normally called a two-particle one-hole state. Because at the end, we need to conserve the number of particles. We are assuming in our reaction here, or our mechanism which we put in here, that the number of particles, the total number of particles is conserved. That's an assumption which is pretty common, unless you have the Hamiltonians which do not conserve the number of particles. There can be physical processes like that. And for those of you taking QFT, you know that there may be physical processes which do not conserve a specific set of particles. So this could be a one intermediate state. And you see now I take away one with a whole state, but then I create a new one. So the action of these two guys is actually to bring in a modification of this one, but that is still an n particle state. But then I have this one, which brings me to a one particle state at the end. So this is one possibility. I could also have another possibility, which could be an A, let's call this an AB, but then I could have an AJ, AI of phi 0. So this is a two-hole, one particle state. And then I could continue, but you will see that quickly that in order to conserve the number of particles, these are the only possibilities to second order. You can list many, many other possibilities, but if you wish to conserve the number of particles in the system, and you also want to have overlap matrix elements which are non-zero, these are basically the contributions which you get to second order. So what does that mean? If I take the first case, what I'm going to do now, if we just list these 1, 2, and 3 here as possibilities, what I will be getting when I'm setting things up is a phi 0 of A, and then I'm looking at the one body operator. So I'm just taking the operators now. And then I would have an intermediate state, which is an AB dagger acting on phi 0. So that is one of the matrix elements we are looking at, okay, with one of the intermediate states. And we see that this one is something which will give us something which is non-zero. So I can actually have an intermediate states where B is now a state which is not the one we are targeting, this A. It's a state which is different. So this would simply give us a term which goes like A, and then I have this F and B here. So if I have an orthogonal basis, where this basis is an eigenbasis of H0, which is pretty common, then this is just given by the sum of I less than F, and then I have my A of the AI, V, and BI anti-symmetrized. So that specific term is going to give us the following contribution. So that will give us a delta E to second order, which is given by the sum over these intermediate whole states. And then I'm simply going to have a matrix element of A of I, and then V of B of I. So there's a sum of a B as well. And then I'm skipping this anti-symmetrization term. And there's going to be an energy denominator, which is epsilon I, epsilon A minus epsilon I minus epsilon A. So diagrammatically, this is going to look like this. And in principle, this is actually going to be given by two different sums. So, but they are actually ending up being the same terms here. And I would have a state B here. I have a state A coming in and a state A here. Actually, this should be a B here. And so the energy denominator is going to be given by epsilon I minus epsilon B. So this is one specific contribution which we have to the energy. And if I take the two-body term, I would have a phi 0 A, and then I would have an AP dagger AQ, AS, AR of AB of phi 0. And you see that for this specific case, this has to be equal to 0. Because we are left again with an operator which is uncontracted here. So we have these terms here, which then give rise to a 0 here with a normal ordered Hamiltonian. So this could be one specific contribution, which we have to second order. Now, if we want to also include the external potential, we could replace some of these terms with the external potential as well. Okay, so the next thing which we are going to do is to look at, after the break, we are going to look now at the contribution where we have a two-particle one-hole state. So if we have a two-particle one-hole state, we are going to have a term like this, AA, and then I'm having AP dagger AQ, and this is going to act on a state AB, AC, and AI, acting on phi 0. And here you will actually see that this is a contribution which is going to be equal to 0. So the only one which is of interest now for us is actually this with an AP, AQ dagger, AS, AR, and then AB, AC, A of I acting on phi 0. So I leave that as a small exercise during the break. So we take a small break, and then after that one, we're going to see what kind of contribution we are getting here. So these will be the two terms which we need to look at now. And then what we are going to see after the break is that the contribution we get is something which looks like this. So it's going to be an interaction, and then we are going to have a whole state. We're going to have a particle state B, a particle state C, and a whole state I. And there is an incoming state A and an outgoing state A. So this represents the interaction between this incoming particle and the reference state, and which then defines the medium of the system. But let's see what kind of contractions pop up when we meet again after a break. So let's just stretch legs for some 10-15 minutes. So the one of the reasons why I bring up these things is that we have this element of repetition as well with many-body perturbation theory. And if you then look at the possible contributions which you can have when you have a two-particle one-hole state. So the state which we defined here is now a two-particle one-hole intermediate state. And another reason why I bring this up is that in case you now have two particles on top of your reference state or your reference vacuum, then you could easily create a two-particle two-hole excitation. You can actually have a four-particle two-hole excitation as an intermediate state, and so on. So you see the basic machinery here is something you can extend to many particles. But now we're just thinking of this simple physical process which we want to link to the one-body Green's function. And for the one-body Green's function, this is a way to set up the way one particle interacts, either with nothing or with a medium, which we can define as we want. So in this specific case, when you look at the kind of contractions we can make, you see now that in this particular case, for the one particle, one hole operator, there are actually no contributions which will give a final result, which is non-zero. And you can easily see that when you perform the contractions here, because you have a contraction of, if we now just look at it, you can have a contraction of this type here, that is fully allowed. And then we could have a contraction here to that one. And finally, we could have a contraction as well with this one. But in this particular case, when we are setting up an intermediate state, we have required that these intermediate states do not belong to the states which we have defined here. So we would like this C to be different from this state A. So this is a typical state. The state which we create now here is going to be a state which does not have any contribution from this specific state here. So that would be a definition of that. But still, this could be one possible contraction which we could have. If we allow this one, because if we look at the two particle one, so in case we insist that C has to be different from A, then this will be a zero contraction. However, if we now allow this C to be equal to A, then you see now that in this case here, we have a two particle one hole state, which is being created. But then when we take this one and that one, that gives a two particle state on the brass side. And then we have a one hole state here. So this term here can actually give a contribution which is non-zero. So this is possible. On the other hand, the more interesting ones, so this is going to give us contributions which look similar to what we had before of this type here. But then, if we now look at this specific contribution here, this is a little bit more interesting because it's going to give us a slightly different type of contributions. And if we now look at the possible contractions which we can have, so we can contract this one with that one, and this one with that. And then we can contract this with this one. That's a particle state. And finally, we could then contract this with that one. So these are all possible contractions. And when you then collect everything, you will get a total contribution from the two-body interaction, which is going to look like, and I'm actually just setting up the possible contractions, but at the end, you're going to get an expression which is going to look like as follows. So there's going to be a sum over A, C, and I. No, sorry, B, C, and I. And there's a factor of a half because you have two fermion lines which start at the same vertex and end at the same vertex. And then I have A and I, or B, and then I have B, C as intermediate states, B, C, and B, and then I have my A and I here. And then when I look at the energy denominator, this is actually going to be equal to epsilon A plus epsilon I minus epsilon B minus epsilon C. That's going to be the final expression for this specific diagram. There's a sum over B here. So let me just be a little bit more careful with the writing here. So this is a B, C, and I. So what we produce now is a two particle, one hole intermediate state. And if you look at it, this is the state which we are producing. So this is a two particle, one hole excitation. Now there is a further term, and I leave that as a kind of exercise to you guys. There is another term which is going to look like this. So we have two hole states, but now we have this being contracted, the particle is being contracted here at the final vertex. So the diagram here, when we put labels, is going to have A, and it's going to have a state I, a whole state I, and a whole state J. This has a B. And this diagram here has also a factor of a half, and it sums over I and J and B. And then I would have a outgoing state I and an outgoing state J. I have a B, and then I have my A and B. And then I have my A and B here, and V, I, and J. And this has a epsilon I plus an epsilon J minus epsilon B minus epsilon A. And the diagram here is a so-called two-hole, one-particle state. So we produce as an intermediate state a two-hole, one-particle state. So if we collect everything here, so collecting all the terms of the self-energy, so this sigma to second order is going to be given in a diagrammatic way in terms of this diagram, which we have. So we have an A, And now I'm leaving out all the terms which could arise due to the inclusion of an external potential. So I'm just leaving that out. So if the motion is confined to move, the particle is confined to move in let's say, harmonic oscillator potential, I'm just leaving that term out. So I'm just including now the terms which come from the two-body interaction. So I would then have a term to second order, which is going to look like this. So we will normally put different indices here. So we would have an intermediate state B, and then we have an A and A. You can change the incoming states. It doesn't need to be in the same state. It could be an A to a C or any other types of final states. So if you look back at the image which we set up in the previous lecture, if you look at this type of reaction, you could actually think of this as one initial state, and then you would have a final state which could be different. Now we just looked at the transition from the same state to the same state. So if you then collect these terms in a diagrammatic way, you would get the next contributions, which looks like this. So we have an A, and then we have an I, and a J, and a B here, plus the two-particle one-hole term. So these are all terms which you can calculate with many-body perturbation theory. And then you could use these as an approximation to the self-energy, and then define the Green's function in terms of this approximation to the self-energy. Alternatively, you can actually resum specific classes of diagrams. So if you now look at the diagram, let's say we take a look at this diagram here, what you could do, and this is a set of diagrams which you can resum, which we barely discussed some time ago. We call it the Time-Dankov series of diagrams. So if you now look at this specific term here, what you could think of is to resum to infinite order. If you take this diagram here, there's something which is called the Tam-Dankov plus or RPA. And these are contributions which you can sum to infinite order by a resummation of a geometric series, which technically leads to a matrix inversion problem. So what you could do then is actually to sum this type of one particle, one hole excitations. I'm just drawing it like this without putting labels. What I'm doing now is just I'm pointing to extensions to what we have done here. So this type of diagrams can actually be resummed to infinite order. And what you would see then is that this is often rewritten as, and you would have a bar like this to indicate that you have resummed all these diagrams. And then you have a one particle, one hole excitation here. And then at the end, you have the final term. So this is something which, when you use such a resummed interaction, then you have to be a little bit careful when you calculate the self-energy, because then you should avoid including in the self-energy terms like this one later, because they would just be counted in this contribution here. So these are diagrams which you can actually sum to, or contributions which you can sum to infinite order. Similarly, you have another class of diagrams which can be summed to infinite order. So you would have the two particle diagrams plus two hole diagrams. These can also be rewritten in terms of geometric series. So if you look at the two particle case, this you would start with something like this. And then you have the intermediate states here. So I'm just pointing to future topics here. So this is a two particle intermediate state. And then you can include high order terms. if you think back to this T matrix, which we discussed last time, so the T matrix would represent typical, if you now just allow for scattering into so-called continuum states, then these two particle states could represent continuum states. And this is something which normally can be solved numerically pretty easy by a matrix inversion. You discretize the momenta, and then you set up the matrices and use Gaussian quadrature to perform the integrations. And that ends up, as we discussed last time, from a practical point of view, in terms of matrix-matrix multiplications and the inversion of a matrix. So these can also be resummed. And then what you will typically see then is that this is defined in terms of a matrix element like that. You have to be a little bit careful with what you mean by this type of renormalization. Because I can also combine two whole and two particle diagrams. And these are diagrams which can be summed to infinite order. So that my series, so this guy here, this one, could also include all two particle, two whole, and two particle, two whole contributions to infinite order. It could be given by this term in the beginning. I could have this one. This is a particle case. And then it could include this term. This is a whole case. And I'm not specifying the external legs because the external legs can be wholes and particles. And then I can sum these to infinite order. So there are actually types of diagrams or contributions which can be summed to infinite order, and they can serve as a way to renormalize the interaction itself. And if you're dealing with systems like electronic systems in solid state physics, if we go back to the electron gas, then these terms here become very important. And if you're doing semiconductor physics, nanotechnology, etc., you will often hear about the TDA and RPA resummation, because that takes into account one particle, one whole excitations to infinite order. And that is, in a way, it's meant to mitigate the long-range part of the Coulomb interaction and the divergences which the Coulomb interaction will give you order by order in perturbation theory. If you, on the other hand, deal with interactions which have a strong, repulsive, short distance part, then you could renormalize this interaction here by summing these two particle interactions to infinite order. And that is a way to mitigate an interaction which becomes extremely repulsive at short distances. So the kind of physics you have dictates also the kind of renormalization scheme, or this is not exactly renormalization, but a resummation of specific many-body contributions. And for those who have taken quantum field theory, you're probably familiar with the renormalization of the charge, leading to an effective charge of the electron, and the renormalization of the electron mass. So this quantity, the self-energy, which we have been calculating here, it's called the self-energy because the particle is interacting with itself and in the medium. And it's often also called the mass operator because you can use this one to define an effective mass for the particle. So these are just digressions at the end of the semester about things which you can do with this kind of Green's function formalism. So if you look at the final oral examination, one thing you could do, and this is normally what many people have done, is to go through, let's say, the basic elements we've gone through this during the semester, like second quantization, the anti-commutation rules, Wick's theorem, just mention that briefly, and then discuss the many-body theories, which we have gone through, like full FCI, configuration interaction theory. And then you would typically discuss Hartley-Fock theory, which is like a kitchen item. And then approximations like many-body perturbation theory. And then if you wish to say something about Green's functions, if you wish to explore that a little bit more, you could do that. And then you can illustrate the theories by bringing up the examples which we discussed in the midterms. So you could focus on the Lipkin model if you want to, and you can add calculations with many-body perturbation theory to the Lipkin model and do a presentation using the Lipkin model to illustrate the theories. Or you could take the pairing model here. Or if you have time and have some other models you've been studying, you could do that. You can use everything you've done in the semester here. So that means that when you make the presentation, in the presentation, you should use slides. So because if you try to use the whiteboard or the blackboard, you will just be able to write some few lines and then time is gone. So you should make a presentation 25, 30 minutes where you actually go through the things we've gone through during the semester. And then we will ask questions. 15 minutes typically. So I hope that is a format which takes away some pressure with the final exam as well.
Sort of questions I mean, do you have an example of sort of question types we will get in 15 minutes? Will it be like derive this and this?
No, we will normally not do that. It will be more conceptual questions. Say again?
Yes.
Yeah, I know. Yeah, that's okay. But it could be more the interpretation of the results could be one thing. So if you discuss, let's say, the results with a pairing model, we could ask you about specific results, like what happens when you take away the 4-particle, 4-hole part in a diagonalization. How much of that do you recover when you do many-body perturbation theory? What happens when you increase the size of this coupling constant or this interaction term, this G? And what would you expect? Why do you expect that? Why do you expect perturbation theory to break down? Things like that. These would be typical questions which we could ask. Another question is, which goes back to the more conceptual one with the creation and annihilation operators. And that is, how do we bake in the Pauli principle here? Because when you write down the Slater determinant in the number representation or in Fock space, you don't see this explicit Slater determinant with where the anti-symmetrization is explicit. So how do you recover anti-symmetrization? And that the answer to that one is very simple, the anti-commutation rules. But these are things which you often don't think of, right? Because you get so used to think of the formalism that you forget about the wood because there's so many trees which confuse you. And this is a typical thing which has confused people. You start with everything in standard first quantization, is a bad name, by the way. And then it's very easy when you see a Slater determinant that this actually is a way to implement the anti-symmetry. We could also ask questions, is the Slater determinant the true wave function? So you get so used to think of a Slater determinant, you think of this as the solution to the interacting problem, right? But it is only an approximation to your wave function. So this would be the kind of more overarching understanding, right? So you split your Hamiltonian in an unperturbed part, which you can solve. You get an unperturbed single particle basis, and you use that to make an ansatz for a many-body system. And then you can use the orthogonality of the single particle basis, which leads to an orthogonal basis of Slater determinants. And with that one, you can expand the true solution in terms of an orthogonal basis. But many people tend to think of like this ansatz for the ground state or the Hartley-Fox solution as almost the answer. So if we ask you about things like that, and then you should just say, hey, this is just an ansatz, right? Don't you think I know my many-body physics? I'm almost offended if you ask me a question like that, right? So, but these are the things these are the more overarching things, right? And as you've seen through the semester, we actually build up a way to represent a many-body system in terms of a single particle basis. This breaks down the whole machinery which we have discussed here, in a way breaks down when you have strongly interacting systems, because then a mean field doesn't make sense anymore. Then many of the methods like many-body perturbation theory, Hartree-Fock theory, are not that useful. And that would lead to other methods like Monte Carlo methods, variational Monte Carlo, diffusion Monte Carlo, and other many-body methods. And these FCI would converge slowly. That is something you would see if you actually have a very dense set of single particle states. So that means that it's easy to excite from the ansatz for the ground state to a one particle, one hole, two particle, two hole. So then you would have a huge mixture of states. And if your matrix is large, then these eigenvalue solvers converge slowly. If your matrix is small, you will diagonalize easily. Yes, yes, yes. But the problem is that if you have billions of Slater determinants, your basis is huge, then you use iterative solvers like Krylov methods or Langsdorff's method, if the matrix is symmetric. And these methods converge to the lowest states and the highest lying states, but their convergence is very, very slow if this Hartree-Fock ansatz is a poor one. It will ultimately converge, but maybe not in your lifetime. Or it will converge slowly. So there's always the kind of, it's the hope here is that you see the pros and the cons of the methods, the limits and their appropriate usefulness, which in what we have done here is very much tailored to systems where single particle degrees of freedom are relevant as a way to describe the system. Also keep in mind, and don't make that error, that there are single particle energies as observables. So it's very tempting because we have discussed things in terms of single particle properties. You do the Green's function, and actually the Green's function, if you go into the slides, there is a discussion of something which is called spectral functions and spectroscopic factors, which can be related to experiments. And then it's very tempting to say that these are almost like observables. What you're dealing with is complicated many-body systems. And we are extracting information and interpretations. And like everything which I did here now with this kind of simple examples, if we go back a little bit here. So one of the reasons why I brought up this example is that these are complicated many-body systems. But we are making a kind of picture where we think of, let's say, a proton which is colliding with oxygen-16. It gets picked up, you form an intermediate state, and then this is not stable. And then this fluorine-17 decays by emitting a proton. So proton emission is actually a physical process which many experimentalists study in nuclear physics. You could replace this again with an electron which is being captured by a semiconductor on the surface of a semiconductor. There are point defects, like we are realizing at the Center for Material Science. And then you can trap the electron here. And then after some time, if this well is very shallow, then a small disturbance can actually lead to the electron leaving the system. The description with a single particle basis is also very useful if you're doing bosonic systems, especially weakly interacting systems of bosons. If you go to strongly interacting system of bosons, then this ansatz with a single particle picture also breaks down, because then you're having strong correlations again. And an example there, if you're looking at the phase transitions, if you do many-body physics at finite temperature, then the phase transition for liquid helium to superfluid helium is a system which is strongly interacting because you have helium atoms which repel each other at short distances. And for that system, a mean field picture doesn't make sense. But if you go to weakly interacting systems of bosons, and you look at Bose-Einstein condensation, which I think Vebjørn is studying, then in that case, you can actually use mean field methods. And the Gross-Pitayevsky equation, which you are studying, Vebjørn, is an example of a mean field equation. And in that case, this single particle picture makes sense. So I keep always a critical eye on everything we've done. You've got a kind of start into many-body physics. Many of you may actually want to work with finer temperature or time dependence. So I hope the kind of lectures we've gone through here can serve as a starting point for studying these more specialized topics. We have also not gone into that detail into the Green's function machinery, which in itself is a many-body course by itself. But hopefully the formalism which we've gone through allows you to go into studies of these type of many-body methods as well. This is going to conclude basically what I wanted to say. There is more information in the slides, which I put up. So if we go back to the slides, if you have time, this contains a little bit more about single particle Green's function, which we also discussed last time. But if we now move on a little bit, I just wanted to point to some of the topics which we haven't covered. And this is just a little bit about the Green's function, which we also discussed in the Heisenberg picture, and the so-called Lehmann representation. But there are things here which I wanted to link to, and these are quantities which are called spectral functions, which are extremely useful. And the spectral function is normally interpreted as the probability of adding or removing one particle in a state alpha and leaving the residual system in a specific state with a given energy. And these are quantities which can be related more easily to experimental observables. And this spectral function is often used to define important quantities like the one-body density. So the one-body density measures the probability of finding a particle at a specific in a specific position in a many-body system. And they can be directly related to the Green's functions, and again, directly related to these spectral functions, which we haven't covered in detail. These are interesting technicalities with Green's functions, which often tell you why Green's functions are so interesting, because there is a shorter route to compare with the experiment. If you do, for instance, copper cluster theory, which we haven't discussed, to calculate other observables than the energy is often very clumsy and cumbersome. A Green's function, on the other hand, if you have it, you can actually use that one to calculate easily, for instance, some rules for the energies, which are extremely useful. These are conservation laws. And you can relate immediately the Green's function to that. And I just invite you to take a quick look at some of the machinery here, which we haven't had time to cover, if you're interested. Else, this textbook, which I mentioned by Dickoff and Van Neck, gives a good discussion of let's see, where did that disappear? Just take this one away. I thought I had it here. Let me see. Yeah, the textbook by if you're interested in Green's function, the textbook by Dickoff and Van Neck is a useful starting point. We also have in the lecture notes or in the GitHub address, there's the link to the textbook by Nagel and Hollande, which is a little bit more advanced than this textbook here. And also never hesitate to ask questions about the usage of many-body theories. And in case you're studying many-body problems and you have questions about which method should I use and which theory should I focus on, don't hesitate to ask questions.
Could the potential end of the oral exam be that we go into sort of the beginning of
Absolutely, absolutely. So what I mentioned here was the link between many-body perturbation theory and the calculation of the self-energy and Dyson's equation. So if you want to, you can always make excursions like that. So feel free to, for the final, the midterm, I know that many of you are working on density functional theory, and we spent some time on density functional theory, although we didn't go that deep into it, because we wanted to link density functional theory with the electron gas and the way it's normally used in solid state physics and in quantum chemistry, atomic and molecular physics. So if you would like to say something, suppose you talk about FCI, and then you say something about the Hartree-Fock and many-body perturbation theory, but then you could go on a tangent on density functional theory, which is also another many-body method. And if you have questions about the final presentation, I mean, don't hesitate to send a mail, whether this is important or relevant or not. So even if we haven't studied bosonic systems, to you, Björn, I mean, if you want to talk about the Gross-Pitayevsky equation as an example of many-body system, many-body methods, and because that links well with mean field theories, that could be an excursion at the end, right? Okay, I'm going to at least stop the recording here. Where did my